Wasabi, you guys. Welcome to Integration Bee Training for Advanced. I believe we are in 12.1, so meaning that this section is going to be about piecewise integrals. Now, in this part, we're going to be learning about the manual, just manual piecewise integrals. We're not going to get into the sums yet. I'm going to first teach you just like an introductory concept to what these piecewise functions are. Okay, so our three main piecewise functions that you must be familiar to. So first off is the floor function, right? You've probably have seen this somewhere in like integration bee videos, or some integral problems, or like Romanian mathematical. I think it was Romanian mathematical masters, something like that. But you see these a lot. Floor functions, sometimes a ceiling function, and then even scarier, a fractional part. Okay? Now, don't be scared. It's actually not as bad. Not as bad. Okay? So what are these functions? So all it is they're pretty much, they just kind of round. So for example, like a floor function means that you just kind of round it down into an integer. So what this would equal is, because it's 3.14, the floor function of pi is going to equal to 3. Okay? The ceiling function rounds up. Okay? So rounding down, we're rounding up. Okay? They're both forcefully rounding a number into an integer. So because this would be 3.14, we round it upwards, meaning that this would equal to 4. Okay? That's all it is, right? If I were to go with E, right, 2.71, this is going to equal to 2. And then, of course, the ceiling function of E is just going to equal to 3. Okay? So what you can also do is, you can also say that for any ceiling function, this is literally equal to the floor function plus 1. That's literally what this is. Okay? Right? Because the floor function, you just round it down forcefully, and then the ceiling function, you just round it up. Okay? And now, what about fractional parts? What is fractional parts? So a fractional part means that you're just taking the decimal portion of the number. So pi is a little nasty example because it is an irrational number, but this would equal 0.14159 whatever. Okay, right? If I take the let's say like a number of 1/2, the fractional part of 1/2, it's 1/2 because that's the fractional part of 1 plus 1/2, right? If I had something like 4.8, the fractional part of 4.8 is literally 0.8. The fractional part of 1.7690 or something. I don't know why, I'll put a 1. Then this is literally just equal to, I'll put 0.76901, right? Literally just the decimal portion, the fractional part, okay? And yes, we can also write this as a formula. A fractional part is literally the whole number minus the integer of it. Okay? All right. So now that you're familiar with what these functions are, let me show you geometrically so that you understand better what on earth you're integrating. Okay? So let me first show you the graphing of each of these functions. So geometrically, let's say if we have the ceiling function, right? And we have something like from 0 to 1, 2, 3, 4, whatever. Okay? I'm just going to go up to like 1, 2, 3, 4. Okay? And so what this would look like is, let's see, from any numbers between 0 and 1, this is going to be 0, right? Because we're rounding it down. Okay, we're rounding it down. And then at 1, if we plug in x equals to 1, the floor function of 1 is just 1. So our actual value is here, and this would be a whole. And then from between 1 to 2, every number is just going to round down to 1. And then if we plug in 2, x equals to 2, the floor function of 2 is just 2. So our real value is here. We have a whole here. And then it's just going to continue doing that pattern. Okay? So this is for the floor function here. Okay? This is for the floor function. I'm just going to color code this. Okay. So that's for the floor function. Now, for the ceiling function, it's technically similarly the same in a way. So like if you plug in whatever here, right, plug in 0, it's going to equal to 0, right? But if you plug in any way higher, it's going to round up to 1. So it's going to round up to 1. Okay? And then anywhere higher than 1, it's going to round up to 2. Right? Anywhere higher than 2 is going to equal to 3. Okay? So that's, and then so forth. It's going to go higher. Okay. So that is that. So this is the ceiling function. Okay? It just kind of stacks on top of the floor function, which makes sense, right? Because it is a plus 1 more. So what does the fractional part look like? What does the fractional part look like? So what I really like about fractional parts is that this function, right, it doesn't, I mean, it's just a decimal portion of it, right? So all it is just, okay, it just takes the decimal, and if it equals to 1, then it's equal to, it just becomes 0. Okay, if it equals to a whole number, it just equals to 0. So there's a whole right here. And then, okay, 1 between 1 to 2, I mean, it's only taking the fraction part. And then when it equals x equals to 2, it just equals to 0 because there's no decimals. So there's a whole here, and it keeps going, and then going, and then going, etc. Right? Notice that it repeats. What does it mean when a function repeats like this? It means that this function is periodic at 1. Okay? So keep that in mind. Okay? You'll see why that's such an important fact. Okay? This function, the fractional part, is a periodic function. Okay? Cool. So when we integrate functions like this, when we integrate such functions, you know, it's kind of like it's like a stack of rectangles. Like if I was to integrate the ceiling function, I'm just adding up rectangles, integer rectangles. So it'll be like what? This would be, if I were to integrate like from 1 to 4, right? And I have like the ceiling function, then I'm having this area, the area of the rectangle here. This is like 2 plus 3 plus 4, and notice that it's becoming a sum. Okay? But for now, in this section, we're just learning the manual, learning to integrate manually rather than using the summation. Okay? All right. I think we're ready to get started with some integral examples. All right, our first piecewise integral here. So we have a floor function and a ceiling function here. So how do we solve this? So it's like the absolute value. If you remember your beginner training of how when we have absolute values, we have to split the integral. So that's literally it's exactly what we're going to do here, right? We're going to split the integral, and it's because, you know, these are piecewise functions. So from 0 to 1, between 0 to 1, x will always be equal to 0. Okay. And then from 0 to 1, this will always equal to 1. Okay. How about from 1 to 2? At 1 to 2, this is gonna equal to 1, this is gonna equal to 2, so it's 1 plus 2. Okay. And then I'm just gonna do some shortcut here. Okay, 2 plus 3. From 3 to 4, we have 3 plus 4, etc. Well, I mean, our last one. But you get the idea, right? Okay, this is 1, this is 3. Let's see, 2 minus 1. Oh, okay. Each interval of the bounds is just 1, right? 3 minus 2 is 1, 4 minus 3 is 1, 5 minus 4 is 1. So all we have is just 1 plus 3 plus 5 plus 7, and then our last one is 9. Okay, and so this whole sum is equal to 25. So our answer for this integral is 25. Okay, so again, this is how we manually integrate piecewise functions because, well, they're piecewise functions, right? You have to split it up. You have to split up the bounds. Okay. Okay, now we have a fractional part, but then there's 256 here. So what do we do? What do we do here? How do we integrate this, right? I mean, you can turn it into, this if you want to. You can. It's just a pain to manually integrate it with 256 times. So maybe not. Let's see. If we could. Let's see. What would it look like? Let's see. I mean, it's periodic, right? This is a very bad graph drawing. Oh my god. Okay. So, and it's periodic by 1, right? It's periodic by 1. So for every 256 times, we have like this region here, and this region here, and this region here, and this region here. Okay, interesting. So we're gonna add up this triangle. So what this really equals, what is this area here? So that portion, that area is literally 1/2, right? But that's from 0 to 1. Okay. And then we have to go from 1 to 2, and then 1 to 3, 2 to 3, and 3 to 4. Up to 4, we have 4 triangles. Okay. And so what we're doing is we're going to go up all the way up to 256. So up to 256, our total area equals to 128. So our answer is 128. Okay? Our area, the total area of each triangle, is 128, and that's what this integral equals. Okay? I know it's like, it feels forced graphing, but I feel like this is a lot less complicated to understand. Okay? So let's say that we cannot use forced graphing, because like I said, graphing is like last resort, right? And of course, we don't know what the graph of a squared version of fractional parts, like what does that even look like, right? Now it's different, and it's like, it's hard to visualize what the graph is because we're not graphing calculators, right? So how do we solve this? Without graphing, how do we solve this? Well, remember that a fractional part is periodic. So because it is periodic by 1, it is periodic by 1. So from 0 to 1, and then 81 times, because it is periodic by 1, right? If it was periodic by 2, then it would be from 0 to 2, and then it would be like 81 divided by 2. Okay? But because this is periodic by 1, it goes from 0 to 1, and we have multiplying this integral 81 times. Okay? And now going back, we have this integral now. Okay. So what now? So now that we've put in our simplified our bounds, you can now take away the fractional part, and now this is exactly what it equals. Okay. And now you can go ahead and integrate. So thanks to periodic functions, you can do this. So now we can just straight up integrate this easy integral. This is 81 x cubed over x cubed over 3 from 0 to 1, and then we end up getting, that's like 27. Yeah. So our answer is 27. Okay. We are allowed to do this because of the periodic function property. Okay. So now we're really gonna have to manually integrate this. Okay, definitely no sums here. Definitely cannot do sums because we have like a floor function inside of a floor function. So it's like a chain. Okay. So how do we manually integrate this? So again, it differs by integer intervals. So from 0 to 1, we have x plus, we're going to start slowly, and then the inside of this floor function here, from 0 to 1, this is 0. Okay. So that's the 0. Plus from 1 to 2, x plus, and then we have 1. Okay. And then again, this is going to be just x, and then that's also going to be 0. And then x plus 0 is also going to be 0. So this whole integral portion here is just equal to 0. Okay. I'm just going by fast just to prevent such long time. Okay. So here we have x plus 1 now. All right. X plus 1. So what do we do when we have an x plus 1 inside? Then that's no worries. What you can do is just simply do u equals x plus 1. We're not going to overcomplicate things. We're not going to overcomplicate, graph thinking and stuff. No, we're here to speed integrate. So with this, u equals x plus 1. Okay, we have from 2 to 3. Remember that u minus 1 is equal to x. And so this x here is u minus 1 plus the floor function of u. And now this is equal from 2 to 3. This portion is equal to 2. U minus 1 plus 2. Now this is equal to u minus 1 plus 2. That's u plus 1. You already know exactly what to do next. You u sub again, right? Let w equal u plus 1, and you get 3/4 w dw. And over here, what is this? From 3 to 4, the floor function is always going to be 3. So we have 3, 4, 3. And so the answer is just 3. Because 3 times 4 minus 1 is 3. I'm sorry, 4 minus 3 is 3. 4 minus 1. 3 times 4 minus 3 is equal to 3. Okay, I'm just going by fast. All right, so that's it. That's how you integrate manually. Not that bad. It's not that bad. You just have to get very comfortable, focusing on the domain. Okay. All right, let's do 2 more examples. Don't freak out. Do not freak out. It's okay. I know this looks intimidating, but I do have to prepare you for such realistic integration bee problems. But here, I see that we're going to have to do things manually. Okay, so when in doubt, when this looks complicated, you can simplify with using the formulas. So fractional parts, this looks very complicated fractional parts, so I'm going to turn that in terms of floor functions. So now turn that in terms of floor functions. Now it's easy to see that, oh, well, from 1 to 2, this floor function is just going to be 1. So this will equal to x minus 1 squared over x dx. And that's it. That's literally your integral. So integrate this, you get, let's see, from 1 to 2, you get like x minus 2 plus 1 over x. Yeah. I'm just going to go by just for the sake of time. You know, this is from 1 to 2. This is just going to equal like 2 square ln of 2, 1/2, ln of 2 minus 1/2. Okay, that is our answer. So whenever you know, go ahead and turn it in terms of floor functions, and then use your intervals to just kind of turn it into a number. Because I mean, it's a floor function. It's a piecewise integral. I'm sorry, it's a piecewise function. So you could just turn it into a number based on the intervals. Okay, and thankfully it's just only from 1 to 2, so there was no splitting that we need to do. All right, last integral. So here, it seems like we're gonna have to do this manually again. So let's go ahead. This looks terrifying, so I'm just gonna simplify it in terms of floor functions. So let's go ahead to x minus the floor function of x to the power of the floor function. Okay, so this is going to turn out to be, so we're going to have to do some splitting here. So from 1 to 2, this is going to equal x minus 1 to the power of 1. From 2 to 3, this is x minus 2 to the power of 2. From 3 to 4, this is going to equal to x minus 3 to the power of 3. Okay, awesome. Huh. If I let u equal x minus 1, if I let u equal x minus 1, I get from 0 to 1, u. If I let w equal x minus 2, I get from 0 to 1, w squared. And if I let t equal x minus 3, I get from 0 to 1, t cubed. Oh, would you look at that? This, if I could literally just add these together because they have the same bounds. So I could just add them up like this. This is literally what it equals. How amazing is that? And so now with that, this is all equal. I'm not even gonna simplify this because I hate fractions, but just by this, the answer is 1/2 plus 1/3 plus 1/4. Okay, and that's it. Awesome, cool. So that's how floor functions work, ceiling functions, and fractional parts. So hopefully you got a good grasp of the beginner concept of this. So definitely, if you need to, you can rewatch this video just to gain a better, a review of these functions and how it works for integrals. And then you can go ahead and practice, try solving these integrals on your own. Okay? All right. I hope that was helpful. Thank you guys so much for watching, and I'll see you guys in the next part.